Here I'm going to not only talk about the shell method and teach how to approach the shell method and set those up, but please listen to the beginnings of these problems. I'm going to take you through my mindset of what I'm thinking of determining whether it's going to be a dx problem or a dy problem, which is going to determine whether it's going to be a shell method or a disk method. I never look at the problem and say, am I going to use disk or shell on this? How do I know I'm going to use disk or shell? You're already losing if you're trying to do that. You got to look at the picture. You got to look at the equation. The picture or the equation will dictate which way that rectangle should be drawn. And that will determine whether it's going to be a dx problem or a dy problem. And based on whether that rectangle is parallel or perpendicular to our axis of revolution will determine whether it's going to be the disk method or the shell method. All right. So it's just going to seem like the shell method works in this section because it's called the shell method. The disk method work and all the other problems there, but there's certain problems where only the disk method will work. There's certain problems where only the shell method works. Okay, so they don't work all the time, but there's certain problems that only the disk method works or the shell method works. On the problems where it doesn't matter, you can use either or on a lot of the problems there. You just pick one and go with it, and you're going to work out just fine. So let's review. These are the few examples that we're going to do. But before we get to that, let's just kind of review the steps. Okay, so we're going to draw our bounded area. This time we talked about in the understanding video, the part 1 video, you're going to draw a rectangle parallel to the axis of revolution. And then your dx or dy, same as your disk method, that's still determined by the width of the rectangle, same exact thing. If it's horizontal, it's a dx, vertical, it's a dy. And here, the p is the distance from your axis of revolution to your rectangle. Now, when I get the p value, that's going to be the same exact thinking. This section may seem easier to you. One, because you're not squaring a bunch of stuff, but also you already had a bunch of practice to trying to obtain that capital R and the little r. And that's what the P is different than the capital R and little r, but the thinking is the same because you're going to be measuring distances from the x-axis up, from the y-axis over, from an axis backwards or down. And so you're going to use the same 4 big scenarios right there. So let's review those 4 big scenarios. Remember our 4 big scenarios that you're going to use this thinking on the capital R to little r and to obtain the p value. Anytime you're measuring the distance from an x-axis up, that's your y variable. From the y-axis over, that's your x variable. And then anytime you measure from an axis backwards, if this is x equals a number, and you're measuring the distance from an axis back towards a rectangle that's in that area, that distance will always be whatever this number is minus x. You want to start with that. And if you're measuring from an axis downward, that distance will always be that number minus y. If that's like y equals a number, whatever that number is, you're going to go that number minus y. That's the things that we're going to start with. So I'm going to use those same exact thinking to get the p value as we did on the capital R and the little r. All right. The one that's different is the h value. The h value is the height of the rectangle. Just how tall is that rectangle? Now, what I used to kind of teach this a couple different ways, and I think it just used to confuse people. Once I started doing this, it just was, I think, easier for students there. One thing that always works when your rectangle's up and down like that, your h, I want you to start off with thinking top y minus the bottom y. Then it's going to be a dx problem, and we're going to need to switch it in terms of x's, right? But when the rectangle's on the side like that, I want you to think right x value minus the left x value. And then it's going to be a dy problem, and then we'll switch it in terms of y. So the reason for that is just basic. I don't even know if you consider this geometry or just common sense. But if your rectangle is drawn like this, we know the height of that thing is going to be 3. But what we really did, we did the top y minus the bottom y, 5 minus 2. We know the height of this is also going to be 3, but we did the right x value minus the left x value. So that's why I'm going to have you start with those. But just if you got something like this, right, you got to, I just made up those equations. I don't know if those are accurate graphs, but if my rectangle is like right here, see, sometimes your rectangle is right there, then your rectangle is going to be right there, then your rectangle is going to be right there. So that rectangle is going to be constantly changing. And so if it's not the same, like this 5 minus the 2 or 7 minus the 4, then whatever this y value is, whatever this y value is, whatever this y value is, you're going to do top y minus the bottom y to figure out what the height of that rectangle is going to be, right? And so that's where you need to kind of use this top y minus the bottom y, and also just use the variables right there. If it's changing, you use the variables. You could graph both the equations in your graphing calculator. And if you're not sure which is the top one is, remember, you can hit that trace button to determine which one's your top curve. And then you know which is your top curve right there. Then you can go top curve minus your bottom curve. Make sure you go minus the bottom curve. You're putting that whole thing in parentheses. And then you can simplify that. And then you can use that for the H right there. So try to just think, the most difficult part on the disk and shell problems is just obtaining the capital R, little r, and the P and the H value. So once we get that, then we're going to be good. But try to think as the capital R, little r, and the P is the same exact type of thinking to get your distances. And then the H is the height of the rectangle. So that's one difference. It's top y minus the bottom y, or a right x minus the left x. Now, once you obtain that P and the H, when you do the shell method, it helps me if you put down like disk or shell next to the problem, like indicate which method you're using. Because sometimes we could use symmetry and throw a 2 out there when you're doing the disk method right there. But when you're doing the shell method, you got the 2 pi guy out in front, integrated, and then it's just P times H. All right, there's nothing squared there unless you had squares in your original problem there, but it's just P times the H, and then the dx or dy is going to be determined by the width of that rectangle, and then you're going to use the x's or the y's that take you across that shape. Okay, so let's go ahead. Let's do some nuts and bolts examples. And I'm going to take you through right from the beginning how I know to use which method. And again, do not think, am I going to use disk on this or am I going to use shell on this? I do not determine that just by looking at the equation or the picture there. Here's what I'm noticing right away. Sometimes the picture will dictate it. Sometimes the equation will dictate it. All right, so what I'm going to do, I'm going to draw my bounded area. So I'm going to go y equals 4x minus x squared. So my bounded area is going to be doing something like this. And so there's our area right there. And as you look at this problem, the picture in the equation dictates what's going to be right there. You could also set this equation equal to 0 to find out what that intercept is. But I got y equals 0 in that equation. Like if you set it equals 0 and do a GCF real quick, you're going to get x equals 0 and 4. So there's 0, there's 4. So there I have some numbers right there. So that's going to be helpful. All right, and here's the deal. As I'm looking at this picture here, I don't want to draw my rectangle sideways. You never want to draw it from the same curve to the same curve. What you want to do when you draw your rectangle, you want to go from a curve to a straight edge or from a curve to a different curve. That's it, all right? So from a curve to a straight edge or a curve to a different curve. You never want to go from a straight edge to a straight edge, and you never want to go from a curve to the same curve. That's not going to help us, all right? All right, so here's what I'm looking at. I know I don't want my rectangle drawn that way because I don't want to go from a curve to the same curve. So the picture dictates I want my rectangle drawn this way because I'm going to go from a curve to a straight edge, and that's what's going to be good right there. So my picture dictates I want my rectangle drawn that way. Also, when I look at the equation dictates, like if I give you y equals x squared, I can easily make that x equals square root of y. All right, like we did in the disk method notes there. Sometimes we changed it. We use a dx problem or a dy problem. I can't do that on this particular equation. It's not as easy as this where I can do either a dx or a dy problem. So as I look at this equation, I'm seeing x's. I can't solve that get x equals in terms of y. So the equation dictates that this must be a dx problem. And if that must be a dx problem, that means my rectangle must be drawn up and down so that little part is horizontal, making that a dx problem. So that one, the picture in the equation dictates this must be a dx problem. Notice I haven't even discussed whether I'm going to use disk method or shell method on this problem. I haven't even looked at what my axis of revolution is going to be at. I looked at the picture, I looked at my equation, I looked at where that rectangle needed to be drawn. Now I'm going to compare that to the axis of revolution. If it's perpendicular, got to use a disk method. Disk method is the only thing that's got to work right there. If it's parallel, got to use the shell method. The shell method is the only thing that's going to work right there. So since if my axis of revolution had been the x-axis, the disk method is the only thing that's going to work. But since my axis of revolution is the y-axis, and notice that your axis of revolution and that rectangle, they're both up and down, they're parallel to each other, and that's our shell method notes. That's why we're learning this thing, because now we're going to be able to do all different kinds of volumes there. Since it's parallel, that indicates the shell method. That's the type of thinking that you got to do at the beginnings of these problems right there. Don't just decide, oh, am I going to use disk or shell right there? It's an easier problem if I tell you to use a disk method, if I tell you to use a shell method. I'm most likely going to just say, hey, find the volume of this thing. You got to determine on your own which method you're going to use right there. Now, if it doesn't matter, sometimes it won't make any difference. You can just pick a method and go with it. But it will matter. Sometimes people do this section and think, oh, the shell method always works. Can we just learn that one? Well, no, the shell method doesn't always work there. We just talked about, this thing better focus properly, Dane. We just talked about how if this axis of revolution had been the x-axis there, then the disk method is the only thing that's going to work. All right, so once we determined that, now let's say, okay, now I'm determined, hey, I'm going to use the shell method on this problem. And I know that's a dx problem. So now the first three steps are done. I have my area, have the parallel, have the dx or the dy. So now we're going to get the p and the h. All right, so that's where we probably have most of our questions on. So my p value is the distance from your axis of revolution to your rectangle. And you're going to use the same thinking when you're measuring distances. That rectangle could have, that's just one representation of a rectangle. That rectangle is going to go throughout that shape. It could have been there, could have been there, could have been anywhere in there. So when you measure the distance from that axis of revolution over, you're measuring the distance from the y-axis over. Whenever we go from the y-axis over, that variable is always going to be x. So I'm going to just put down an x right there. So the distance from the axis revolution over to the rectangle, that's different. So since it's different, we need to use a variable. From the y-axis over, that's always going to be an x. If this is a dx problem, I get to use that single letter in my integral. This is a dx problem, so I get to use that. I don't need to change it. I don't need to change this in terms of y's at all. All right, that's done. Now I go straight to my h. When the h is up and down like that, I start off with this thinking. This is what will work for me every single time. It's going to be the top y value minus the bottom y value, but it's a dx problem. So this top y value is your y equals 4x minus x squared. There's your top y. And then your bottom y value is your x-axis, is your y equals 0. So you'll subtract that out. So then your h is that 4x minus x squared. So use that thinking, top y minus bottom y, or right x minus the left x, on an h value. And then once you have your p and h, that's the toughest part of the problem. Now we're just going to use this formula. So if I set up my integral using the shell method, this time we have a 2 pi guy out in front, and we're just going to go p times h. So I'm going to take my x times up by the 4x minus x squared. This is a dx problem, which means I need to include that. I need to use the x's that take me across my bounded area. So remember, the numbers attached to integral have nothing to do with what the x revolution is. So on a dx problem, you're going from left to right. What are the x's that take you across your bounded area? You're going to go from 0 to 4. If I just ask you to set it up, that's all I'm asking for right there. But your homework, we're going to set them up. We're going to show that. And then we're also going to just make sure we work through that integral. We know that's an easy integral. You're going to make that 4x squared minus an x cubed. That's going to be an easy integral. Plug in the top number, plug in the bottom number. Make sure you remember to times it by the 2 pi, and then you're good there. All right, but make sure you got situated the little details, right? The shell method is a 2 pi out in front. Disk method is a pi out in front. You got to remember your dx, your dy, and then use those proper numbers attached right there. I'm not going to work that one out for you, but if you want some extra practice, I will tell you the answer to this one. You do get 128 pi over 3 if you just wanted to work out and get some extra practice with those. All right, so let's go to the next example. All right, as I'm looking at this equation, before I even do a picture, okay, as I'm looking at this equation, this is not like this where I can easily make this like x equals something in terms of y. So when I'm looking at this equation, this tells me right away that this has to be a dx problem, which means my rectangle has to be drawn up and down, making that a dx problem. And then I'm going to look at the graph there. Okay, so I just know that going into this thing. I don't look at things like, oh, I'm going to do disk method, or I'm going to do shell method. Forget all that, right? So you got to make sure you look at that rectangle, look at the equation. But now if you graph that, so use your graphing calculator to graph it. That y equals x cubed plus x plus 1. I think it's just kind of doing something like this. So there's our big curve there. And then use all sides of the fence, all right? We also got y equals, so it crosses at 1. So we're also going to do y equals 1 as a horizontal line. We're also going to do x equals 1 is the vertical line. So this is my bounded area. If I use all sides of that fence, that's my bounded area right there. And so this was x equals 1 and y equals 1. This was x equals 1. But if I take that 1, plug into my original equation, figure out that y value, that's going to be what? 1 plus 1 plus 1, which is going to be 3. So I got my nice picture there. And then as I look at the picture, you got to look either at the picture or the equation. The equation we already talked about dictates on this one. If I look at the picture, I can draw my rectangle whichever way that I want. I can draw it up and down because you're going from a curve to a straight edge. I can draw it sideways because I'm going from a curve to a straight edge. So if you're going from a curve to a different curve or a curve to a straight edge, That's okay. As long as you're not going from the same curve to the same curve, or you're not doing two separate rectangles and going from a straight edge to a straight edge, you're gonna be okay here, okay? So the picture dictates I can use my rectangle whichever way that I want, which means that I could probably draw my rectangle where it's parallel or perpendicular to indicate where I can use disc or shell, but the equation restricts this one. The equation restricts this to be a dx problem because I can't solve that and get that x in terms of y. So the equation dictates that my rectangle has to be drawn like this to make that a dx problem. And again, notice I haven't even looked at my axis of revolution. I haven't even decided whether I'm going to use disk method or shell method on this particular problem right there, because it doesn't matter at the beginning. You got to get your picture, you got to get which way that rectangle is going. Now I'm going to look at the axis of revolution. My axis of revolution is x equals 2, which is this vertical line right here. You got to also make sure that x equals a number is a vertical line, y equals a number is a horizontal line, and don't get those switched. Sometimes people put y equals 2, they'll put something up here, something there. X equals number is a vertical line, so make sure you don't mess that up. All right, so anyways, notice that the rectangle and the axis of revolution, they're both parallel to each other. I made them parallel to each other because this is the new shell method section there. I wanted to show you the shell method notes right there. But if the axis of revolution had been the x-axis or the line y equals 4, or y equals -5, then that would have been perpendicular. I would have had to use the disk method on that problem. So don't assume that the shell method is always going to work there just because it seems like it's working on all these problems in the shell method section there. So, but since they're parallel to each other, that's what tells me I'm going to use the shell method. So please don't ignore what I'm talking about here. That's sometimes when people get into a test situation, they can't decide and they always have these questions over there. So watch this video as many times as you need to, but that's where the equation is going to dictate that. Now, since it's a shell method, we're going to need to figure out what the P and the H value are. So the P value is the distance from this axis of revolution back to your rectangle. And again, that rectangle could have been anywhere in there. Okay, that's different. So I'm going to go to that rectangle, to that rectangle. You're measuring from that axis back, and it's different every single time. That's one of our 4 big scenarios. Anytime I measure from that axis backward, it will always be whatever that number is minus x. Start with that, write that down. So it's going to be 2 minus x. Since this is a dx problem, I get to use that. I don't have to change it at all. I get to stop right there. I get to use the 2 minus x in my integral. Since this rectangle is up and down, we're going to go a top y value minus a bottom y value to get that height. And I'm going to purposely not show you something where you got to go right x value minus the left x value, because I want you to see if you can figure that out on your own when you're doing the homework right there. But I think you'll be just fine with that. So when it's up and down, I'm going to go top y minus the bottom y like we talked about here. And then so the top y is your actual equation, that main formula, and then your bottom y, so there's the top of the rectangle is your curve, and then the bottom y, the bottom of that rectangle is that y equals 1 line. So I had y equals that, and then those ones cancel out. So here's our h value. And now when you set up your integral, you have a 2 pi guy out in front, and you're going to go p times h. So just multiply these two things together. It's a dx problem, so go left or right. You're going from x equals 0 to x equals 1. Use the x's that take you across that bounded area. That's a pretty darn easy integral. Multiply that all out, integrate it, plug in the 1, plug in the 0, subtract them. That will give you, if you want some extra practice there, it's going to give you 29 pi over 15 for your final answer. You got to make sure you always remember to times it by the pi or the 2 pi, get those numbers in there, carry down the pi, get those exact answers, leave the pi's in that problem. All right, now I'm not going to give you everything here, but here is where the picture in the equation dictated what was going on. Here, the picture didn't restrict it at all, but the equation restricted it, where that had to be a dx problem. All right, now I'm not going to give you another example here. I'm just going to talk about this one briefly. On this equation here, let's say I have an equation of like y equals 5 over x. I can easily make that like yx equals 5, right? And I can make that x equals 5 over y. So if that's my equation, it's not restrictive like this one where that had to be in terms of x's. It's more like this scenario where the equation of that, I can use a dx problem or I can use a dy problem, which means I could draw my rectangle whichever way that I want. So sometimes the equation won't make any difference. But here on this one, this is an example of when the picture will make a difference. If you're going from like here to here, the picture is going to dictate this one. Now, even if the problem tells you to use a particular method on this one, I need you to use the most efficient method on this one, okay? When I look at this picture, I don't want to draw my rectangle sideways, because if you draw your rectangle sideways, you got to go down here. Down here, you're going from a straight edge to a straight edge if you draw your rectangle like that. And then up here, you're going from a curve to a straight edge. So technically it can be done, but you're going to have to find more intersection points, which sometimes it's not always possible. So sometimes that can't be done, but you're going to have to do two separate problems, do more intersection points, and you're going to have to do a couple different problems right there. Forget all that, right? When I look at this picture, if I just draw my rectangle up and down, that's perfect, because no matter where I put that rectangle in there, it could be right here, it could be right here, you're always going from a curve to a straight edge, curve to a straight edge, curve to a straight edge. There is no straight edge to straight edge, which I told you to avoid. And there's no two separate things where you're going from a curve to a straight edge up here, and then from a straight edge to a straight edge down here, where you got to do two separate problems. So that's what I'm telling you. You need to draw your rectangle like that. Now, then you look at, right? So if you say, hey, there's my picture, there's my rectangle, I want my rectangle to be drawn like that, then you look at where that axis of revolution is at. If my axis of revolution is the y-axis, they're parallel to each other, I use the shell method, right? And then if my axis of revolution is the x-axis, they're perpendicular to each other, then I use the disk method. Even if the book and the homework is telling me to use the shell method on that one, forget that. If it's perpendicular, I'm going to use the disk method. There's a couple in the homework where it tells you to use the shell method because that's the title of that section. I need you to use the disk method on that one. That's the most efficient approach. That's the one that's always going to work for us. That other approach that I'm talking about, it only works sometimes if you could find those easy intersection points there. Because sometimes if you don't do what I'm asking you to do here, you're going to get something that you can't integrate. And if you do what I ask you to do, you're always going to get something that we can integrate here. Okay, so I just want to give you a little preview of that. See if you can kind of figure that stuff out on your own, and then kind of go from there. And that still would have been a dx problem, so I would have kind of used that there. But sometimes you might need to kind of switch that up a little bit and use a dx or a dy. So there's where the equation restricts it. There's where example where the picture will dictate what's going on right there. And then again, you just gotta look parallel, perpendicular, disk method, or the shell method. All right, so that's pretty much all of our new notes. And I just want to mention that there's a lot of problems where it does not matter which method you use. Okay, so if it does not matter, then go ahead, right? Just pick one and go with it. All right. Now, if it does matter and you're using the wrong one, you get 0 partial credit points on this one. Like on this one, if only the shell method works and you're using this method on that one, you're going to get like 0 out of 10 points on that. All right. I can't give you any partial credit points for this. So just really make sure you kind of hopefully paying attention to this video and getting that understanding down. All right. This one here, I'm just going to work it out both ways there. There's a lot of problems on the test where I might just ask you to set stuff up, and there's going to be a lot of problems where I have you work them out the whole entire way through, right? Just to test you over different things there. And I want to test you over like different scenarios and not have to worry so much about the algebra or working the stuff out and worry about the time on there. So that's kind of why I have you do the setup sometimes. This equation, I can rewrite y equals square root of x. I could also solve that. I can make that x equals y squared. And so the equation means I could go either way, right? I can have a dx problem or a dy problem. That rectangle could be drawn either way. When I look at the picture here, I could draw my rectangle up and down because you're going from a curve to a straight edge. I could draw my rectangle sideways because I'm going from a curve to a straight edge. And so that either way, the picture doesn't restrict it at all. The equation doesn't restrict it at all, which means I'm allowed to use disk method or the shell method. So if I just tell you to find the volume and the homework or on a test situation, just pick one and go with it. Or I might just say, hey, let's set it up using the disk method in the shell method. So this might be like the setup for the test practice. I could just say, hey, set them up using both ways, and we'll do that, and then we'll be okay there. I strongly suggest doing a separate picture for each one. If you could do it with one picture, fine, that's good there, but sometimes people mess that up there. So I just do a real quick sketch for each one. All right, so let's just kind of review both techniques here with our volume stuff. So disk method, we would draw a rectangle perpendicular to that axis of revolution of that x equals 6 line. So we're gonna take that shape and just revolve it about that axis of revolution. And then I notice that that's gonna be a vertical width, so that's gonna be a dy prop. And then we're going to go capital R and the little r. So the capital R is a distance from your axis of revolution back to the farther edge of your bounded area. So we measure from that axis back. Remember, that's one of our 4 big scenarios. When we measure from that axis backwards, it will always be that number minus x. And just to attempt to understand again, when you measure from here back, when you measure from the y-axis over, that's going to be that x value. But then the whole darn thing is 6. So if you take the whole 6 minus that x value, that gives us the distance that we want right there. If this is a dx problem, I get to use that, but since this is a dy problem, I need to use what the x is equal to. The x is equal to the y squared, so we get 6 minus y squared right here. And then your little r is the distance from your axis of revolution to your closer edge. So that you're going from straight edge to straight edge, that's the same every single time. That's just 6 minus 4, which is equal to 2 every single time. And so you're set up with your shell disk method. You got the pi guy out front. We're going to go capital R squared minus little r squared. And if I just ask you to set it up, we're almost done. We got to put the numbers attached to the integral. So setting them up. If it's a dy problem, you got to use the y's, bottom to top, the y's that take you across your bounded area. So you're going from bottom to top, y equals 0 to y equals 2. Remember, those numbers attached to the integral have nothing to do with your axis of revolution. You never integrate beyond your actual area right there. So you're going to integrate between 0 and 2 right there. So there's a setup with the shell, the disk method. And if we have to work that out, then I would work that out. All right, and then let's just set it up with the shell method, same type of thing. So if I tell you to use a shell method, that's an easier problem than if you have to decide on your own, right? So you got to use your brain there. You guys are smart enough to figure that out. But if I tell you to use a shell method, that means you draw your rectangle parallel to that axis of revolution. That little part is horizontal, like the x-axis is horizontal, so that's going to be a dx problem. And then we're going to get the p value and the h value. So the p is a distance from your axis of revolution to your rectangle. Remember, your rectangle could have been drawn anywhere in there. I could have drawn it right there. I could have drawn it right there. So you're measuring from that axis back, and that's different. So you got to use your 4 big scenarios. Anytime you measure from that axis backwards, it's the same thing, and it's going to be that number minus x. And then, since this is a dx problem, I get to use that. I don't have to change anything. And then when I do the height of the rectangle, when it's up and down like that, it's always top y minus the bottom y. And if you do have a rectangle on the side, it's going to be right x value minus the left x value. So the top y minus the top y is your equation because it's a dx problem. So you got to switch in terms of x. So I want to know y equals that square root of x minus the bottom y is your y equals 0. So your h then is just going to be that square root of x. And then so when you set it up with the shell method, you have the 2 pi guy out front. And then your formula for the shell method is just p times h. So multiply those two things together. This time it's a dx problem, which means you're going to use the x's that take you across this bounded area. Left or right, you're going from x equals 0 to x equals 4. And there is your setup with your disk method and your shell method. Just to give you a little quick, like if I had to do a right x minus left, let's say I was doing the shell method and my rectangle was on its side like that, and I had to find the height. The height, when it's sideways like that, I would do a right x value minus a left x value. So when I saw that it was sideways and I had to do the height, I would do right x minus the left x. And then the right x would be this side of the rectangle. See how it's the right side of it? That's x equals 4. And then the left x is this curve. The left side of that rectangle is this curve. And so I'd have that, since that's the x curve, but since it's a dy problem, then you got to use the y version of that. So that would be like, it would have been right x minus the left x, but then the right x was x equals 4. And then the left side of that rectangle, the left x, was that equation x equals y squared. That would have been y squared right there. So that's just if I was doing the shell method, it was on its side there. But I purposely didn't give you an example working that out or working out. Just want to see if you can kind of figure out some of that on your own there. But hopefully that helps. And if you have to set it up both ways, we can do that. So please practice as much as possible, and then bring me questions. Just once you get it down, it's all pretty much the same thing over and over again. So you just got to practice to where you're perfect with that, and you get that confidence going that no, you're going to get it right every single time there. So practice till you get that confidence going, and then we'll be good. Let me know if you got questions. Thank you.